record, and I'm gonna let everybody in.
Cool. This is my first time on like a panel, so.
Oh, well, great. Okay, hi everyone. We are just getting started. For those of you who this is your first time here, welcome. And I know many of you have joined us many times in the past, which is always exciting. Let me just introduce myself. I am Lauren Traster. I'm the 4-H Teen and Leadership Program Coordinator here at UVM Extension. Let me just get my slides going. So I'm gonna pop in the chat right now. If you need our live captioning, just click on the link that I just put into the chat. And then if everyone can find their chat box, and I see Leo already has, go in and just introduce yourselves. We love to know who's with us and where everyone's from. Just want our presenter to know, we get most from Vermont, but we do get participants from all over the country, which is the exciting thing about virtual programs. Like KL is one of our regulars from Maryland. Amelia's here from Greensboro. Who else is with us today? It's always nice to just have those introductions done in the chat. Chloe from upstate New York. Nice. See, I told you, we got people from all over. So keep introducing yourselves. We find it to be really nice just to have that few minutes of seeing who's with us. As you are introducing yourselves, I'm going to remind everyone of our protocols when we're here in Zoom. So all of you are muted today. That does not mean we don't want you to share your thoughts and participate. We use the chat box and the Q&A box for these, and we use them very differently. So the chat box is to communicate back and forth with our presenter. She's going to be asking you lots of questions today, have you thinking about things, having you make some guesses. It's going to be very engaging. So the chat box is to stay on topic, communicate back and forth with the presenter, as well as if you want to share your thoughts to others in the chat box. It's just not meant to be, just having side conversations. Matthew, born in California, but in Vermont. Well, welcome. So the Q&A box is for your questions to our presenter. So she'll pause when it's a good fit to answer your questions, but we use the Q&A box so your questions don't get lost in the chat box. So go into the chat, the Q&A box, put your question in there. There's a way to upvote. So you can click on the thumbs up if you like someone's question. That just lets us know more people are interested in that question. We answer every question, so it really doesn't matter where the question is on the list. We will get to all of them before we sign off today. We just ask that you be courteous and respectful to one another. Just make sure you don't create any distractions. And honestly, you're not on video, your mic doesn't work. The only way you can create distractions is in the chat box. So just please remember to be respectful. Stay engaged, participate fully. I know today's topic is going to be really interesting. So before we get to today's topic, I do want to remind you all, actually kind of have an announcement, which is really exciting. We are officially live with our registration for our summer program. So the Natural Resources, save the date and now register. You can sign up for these summer programs. They're going to be in person, which is very exciting. So there's the Natural Resource Management Academy, and we also have a bunch of different workshops through our Summer of Science. So lots of really good science workshops that you can come in person. They're going to be mostly in the Burlington area. We found different outdoor shelters that we can use. There's one in Barrie, and then the Natural Resource Management Academy is in Woodbury. We're trying to get some in other parts of the state, but it's a work in progress. We also are offering 8 scholarships if you want to attend the Citizenship Washington Focus. You need to apply and be accepted to get one of the scholarships. This is a virtual program. You can learn more about that. But the application is due by this Saturday, May 15th. So you can learn about all these different programs at this link website right below here. And I'll put that in the chat a little bit later. So let's get to today's presentation. It's going to be on extreme weather, the climate changes that I can't see because of the box, that we feel. Is that what it says, Charlotte? I wish I could read it.
Yeah.
Our presenter is Charlotte Coburn. So let me tell you a little bit about Charlotte. She is a graduate student at Dartmouth College in Hanover, New Hampshire. She works in the lab of Professor Jonathan Winter, studying changes in extreme weather in the past, present, and future. She uses regional climate modeling and machine learning to investigate the relationship between extreme precipitation and extreme flooding. She completed her Bachelor of Science at McGill University, which is in Canada, in 2019. And in her free time, she enjoys hiking, embroidery, baking, and skiing. So let's welcome Charlotte to the Teen Science Cafe.
Hi, thank you, Lauren. So should I just start sharing my screen or? Cool.
Go right ahead.
Awesome. And thank you so much, everyone, for coming. Okay. There we go. Let me just pull up the chat. Okay. So thank you all so much for coming. And please throughout this presentation, if you have any questions, just drop them in the Q&A. I'll be trying to monitor it throughout. But Lauren, if you notice anything that seems relevant to the moment, feel free to interrupt me in case I don't notice it. So like Lauren said, today I'll be talking about extreme weather, the climate changes that we feel. So I thought I'd start by just giving you guys a bit of background about myself. I was born and raised in rural Quebec in Canada. So for those of you who don't know, that is north of the United States. And just broadly, this kind of influenced my love of nature and my interest in environmental science and the natural world. So I was really grateful to grow up in like such a place that let me get such a connection to nature. When I graduated from high school, I started my undergraduate degree at McGill University, which is in Montreal. And originally I was going to study physics, but then I kind of took some earth science classes, and I just thought that it was a really cool like application of all of these scientific concepts that I've been learning. Like earth science kind of takes physics and chemistry and biology and like smushes it all together and allows you to investigate these real life phenomena that we're all observing all the time. So I found that really interesting. So I got really into earth science in my undergrad degree. I was able to work in the lab of a professor who was a hydrologist. So he looked at like water and water bodies, and I did my honors thesis with him. And I studied intermittent rivers, which are rivers that fall dry at a certain time of year. So maybe like every summer they like dry up or something. And intermittent rivers are really important because of they really help determine the ecology of an area, and they also have impacts on like greenhouse gas emissions and all sorts of stuff. So while I was an undergrad, I actually created the first ever global map of the probability of a river being intermittent, which is what I'm showing you here. So this is just showing for the whole earth, what is the likelihood that a river will fall dry at a certain time of year. You can see like in places like dry, really arid regions like Australia and Africa, the probability is really high. And then in wetter places like the northeastern United States or like the Amazon rainforest, that probability is super low. So this was my undergraduate work, and it was super interesting. I was so grateful to get to do some like really, really cool research. And it really just motivated me to continue on into academic research. So when I graduated in 2019, I came to Dartmouth College, which is right across the river from Vermont, right in Hanover, New Hampshire. And here I'm, obtaining / I just technically defended a couple weeks ago. So I have obtained my Master of Science in Earth Science. So that's really exciting. I'm staying on over the summer to like wrap some things up, but technically I am a master. Thank you, Lauren. Congratulations. Thanks. And so while at Dartmouth, I have been studying extreme weather and flooding, and specifically the impacts of climate change on some of these processes. I was lucky enough to get to work with an amazing group of professors and fellow graduate students, and it's just been a really, really fun and collaborative and creative environment. So I feel really lucky to have gotten my master's at Dartmouth. So I want to kind of start by just asking you guys like what you think of when I say extreme weather. So you can just drop this in the chat. So you can just like throw out an example of like, when I say extreme weather, is there anything that comes to mind? Yeah, Alice says tornado, hurricanes from Amelia, yes. Hurricanes from Alyssa, yes. Floods from Jack, droughts, yes, from Alice. Yes, these are all amazing examples. Tornadoes and hurricanes from Gabby. Yeah, these are all great examples of extreme weather. So I have a list here that I just wrote off the top of my head. This is not like extensive. We have hurricanes from Ezra. Yes, all of these are great. Tsunami, yes. I don't even think of that one, but yes, Alyssa, that is a great example. So you think of, we got hurricanes a lot. Yes, it's definitely an example of extreme weather. Tropical cyclones, which are kind of like hurricanes that make it, further north. Tornadoes we got, yes. Thunderstorms, so you might not think of it, but like just your kind of run-of-the-mill thunderstorm is an example of extreme weather because it's different from like the norm. Hail or like snowstorms are a type of extreme weather that we see definitely a lot here in the Northeast, and I definitely see a lot of in Canada. And flooding, like Gabby said right at the end, droughts and floods, yes. So this is not an extensive list. There are many more examples that you guys brought up, but these are just some of the extreme weather events that I've thought of. And in particular, what I really think about a lot is flooding. So this is a video that I wanted to show you guys. This is from the White River, which is in Vermont, runs through Vermont. And this was during Hurricane Irene in 2011. Someone else said wildfires. Yes, that's also extreme weather for sure. So you can see that this river is like totally flooded. And this was kind of like the most recent, really, really extreme event that's occurred in the Vermont, New Hampshire area. And so the goal of my research at Dartmouth is to understand whether events like these are going to become more or less likely in the future. Because if they're going to become more likely, we might need to start taking into account some adaptations that we can do, like maybe like jacking this bridge up a couple feet. And so the other piece of the puzzle here is that extreme rainfall has increased in the northeastern United States. That's like your thunderstorms, your hurricanes, like any kind of event that brings lots and lots of rain, those have increased. This is a graph that was made, or a plot that was made by a former graduate student who is in my lab group at Dartmouth. His name is Wanping Wang. And he just plotted the annual sum of extreme rain in a year over the 20th and early 21st centuries. So from 1900 all the way up to like 2019, he just said, okay, how much extreme rainfall, so thunderstorms, hurricanes, stuff like that, how much is occurring? And he identified that around the year 1996, so that's like right between where these two lines are, there was a 53% increase in extreme precipitation across the northeastern United States. So this means that extreme rainfall, or we also call it extreme precipitation, has increased quite a bit in the last like 25 or so years. And it's increased to a level that we've never seen before. So this is really concerning for a number of reasons, and the one that I'll be talking mainly about today is for flooding. So the two main questions of my thesis at Dartmouth are, one, what drives stream flow and flooding in the Northeast? And two, how will these drivers and therefore stream flow change in the future? So we need to identify what is causing flooding, what is causing high stream flow, so then we can look into the future to see how all of these processes are going to change so that we can better adapt to, a possible floodier future. So the second piece of the puzzle here is, of course, climate change. So in the chat, I want you guys to kind of say, like, when I say climate change, what comes to mind? I've included some examples here. We have like these poor polar bears, like ice caps are melting. Warming weather for sure from Amelia, global warming from Gabby, Warming weather from Alyssa. Yeah, it's basically the consensus. Things are getting hotter. Jack says utter doom. I hope not, but maybe. Alyssa says mass extinction. Yeah, pretty bleak, but yes. Amelia says more extreme droughts for sure. So yes, all of these things also come to my mind. Gabby says stronger storms. Yes, definitely. So climate change is a variety of impacts. So if we're going to look at like anything going into the future, we have to take climate change into account because, you know, our climate is definitely changing. So I have a little poll for you guys, and maybe some people have already spoiled it in the chat. But my question is, do we think climate change will make extreme weather events like hurricanes more or less likely in the future?
Why don't we just have people write into the chat what they think?
Okay, sure. Yeah, so more likely, as versus destruction of habitat and ecosystems, extreme weather, increased temperature. Yeah. So everyone basically agrees more likely for sure. So this is a plot that is showing the occurrence of extreme weather events all over the world from about 1900 to like 2017. So this is like, I forget the exact threshold that they used, but like, I think it's events that caused like $1 billion in damage or something. And they divided it into floods, storms, and droughts. Important to note that some of this is just due to the fact that back in the day, people didn't keep records as well as we do today. But also part of it is definitely due to the fact that you know, the volume of these really damaging events is certainly increasing. So we're getting more floods, more droughts, more storms, and it's quite concerning in many places in the world. So I need to alter my second question here slightly to clarify that we want to know how these drivers and therefore streamflow will change in the future under climate change. So we need to find a way to take climate change into account when we're looking at how these floods are going to change in the future. Okay, so I want to start by just giving a tiny bit of background before I dive into like the science. Do we know what a watershed is? No, yeah, that's okay. I wasn't sure, so I just wanted to check so I could explain it if we're not sure. So a watershed is basically like the area around a river. So let's say we're looking at a certain river. The watershed would just be the area where, oh, someone said like Lake Champlain. Yes, I'll get to that in 1 second. But someone says it's like, or sorry, so a watershed is like an area that you outline where any water that falls in that area, so any rain, any snow that falls in that area is eventually going to feed into that river. So the watershed of this river is outlined here in white. So any rain that falls within that outline is eventually going to make its way to that river. So that is what a watershed is. Someone said like the Lake Champlain watershed. Alice said that, and that's exactly right. Watersheds don't only exist for rivers, they also exist for lakes. So the Lake Champlain watershed would be like any rain that falls in that area, that's eventually going to make its way into Lake Champlain. So this is a basic concept of what a watershed is. So for my study, we look at 4 of these watersheds that I've outlined here in black. So this is a plot, it's a map of the Northeast. So we have Maine up here. We have New Hampshire, Vermont, New York. I don't know the rest of these states because I am Canadian. But so this is a map showing the change in mean extreme precipitation after the year 1996. So remember that first graph that I showed you around 1996, we got a huge increase in the amount of extreme rain that is falling on the Northeast. This is that exact same data, but just shown in a map. So we can see that pretty much all throughout the Northeast, we get increases in the amount of extreme rainfall after 1996. So the 4 watersheds I've identified, first of all, in northeastern Maine, we have the Mattawamkeag River. So this outline up here, right next to the letter A, is just saying that any rain that falls within that outline is going to make its way into the Mattawamkeag River. Then we have the Dead Diamond River in northern New Hampshire, the White River, which is right here in the Upper Valley, and then the Shenandoah River down in western Virginia. So these are my 4 rivers, my 4 watersheds. You kind of use the word interchangeably that I'm interested in for my study of flooding. We picked these watersheds because we wanted to look at like a range of latitudes. So we wanted to look at a river that was really far north and also a river that was pretty far south, but still within that kind of northeastern zone. Because we wanted to see whether like a watershed that's really cold and snowy experiences flooding in the same way as a watershed that doesn't get a ton of snow. For this talk today, I'm going to be focusing on the White River because it's kind of close to home and it tells a sort of interesting story. And then also the Shenandoah River, which is further south because it's the one that's kind of most different than the other 3. So I'll be focusing on these 2. So first of all, if we're going to be able to predict stream flow in the future, we need a tool to do this. So we need to think of some way that we can use to predict stream flow into the future. We want to start by predicting stream flow using different climate variables. So do you guys have any idea of like what we could use to predict stream flow? Like another way of saying this question would be like, what do you think is important to stream flow? Like, what do you think helps decide how much a river flows? And the answers are probably pretty obvious. The main answer is probably pretty obvious. So if you're thinking about it, you should just write it. Rainfall, yes, exactly. Rain, precipitation. Yes, good job, Alyssa and Amelia, amazing. So rain is pretty much going to be the deciding factor for how much water flows in a river.
Can I interrupt 1 second?
Yeah, for sure.
You get a question that I think needs to be explained before you go on.
Of course.
Can you just explain what stream flow is?
Oh, of course. Yeah. So stream flow is just like how much water is flowing in the river. So if you go down to like a river near your house and you watch the water flowing by, that is stream flow. And so typically, if we want to measure stream flow, we would measure it as like meters cubed per second. So that means like how much water is passing by you every second. So that is how we measure stream flow. Hopefully that makes sense. And if not, feel free to ask another question. Thank you, Lauren. Okay, yeah, people have some really good answers here in the chat. They say temperature, snow melting, landscape, rain, sunlight, how much water is evaporated. Yes, all of these things are going to be really important for deciding how much water we get in the actual river. So you guys nailed it. You got most of I think 3 of the 4 main ones that I was thinking of, but there are also others. So rainfall, obviously super important because that's just going to decide like how much water is falling into the river and into the surrounding area. Soil moisture is something that is also quite important. So that's going to be just like how much water is stored in the soils because ground can only hold so much water. So if you have really, really high soil moisture, when rain falls, it's just going to like run right off of it and go into the river because it's not going to be able to soak up into the soil. Snowmelt, someone said, yes, is very important, especially in the Northeast where we get tons of snow. And then temperature is also really important because it's going to decide how much water is evaporating from the watershed. So the warmer the temperature is, the more water can evaporate, and the drier the area will typically be. So this is like just a quick graph of the hydrological cycle. And we have, even more factors than what I just listed here. We have evaporation, snow melt and runoff, precipitation, so rainfall. Something I didn't mention is like plant uptake is also important. And then like infiltration, so that's the amount that goes into the ground. So all of these things are going to be important to predict stream flow. So next we use machine learning, which is a type of artificial intelligence. So we want to be able to use things like rainfall and snowmelt to predict what stream flow will be. So we turned to these kind of complex computer programs. And specifically, we use a random forest model. So you're probably thinking a forest like this, but that is not what a random forest is. So a random forest actually looks more like this. And I won't get too into the nitty-gritty of how it works. Basically, all you need to know is that it is a forest of decision trees. But what is a decision tree? So we've already decided that we want to use a couple different things to predict stream flow, like rainfall, snowmelt, soil moisture. I think we said like temperature, plant uptake, all that, lovely, lovely stuff. So we would start by gathering up a historical data set where we have all of that data. So we'd take like a day in like 2002, where we knew what rainfall was, we knew what snowmelt was, we knew what soil moisture was because we measured it. And then we were also able to measure stream flow. And we would get a bunch of days like this where we knew what all of our variables were, and we also knew what stream flow was. So this is important. This is called a training data set, and you want as many different data points in it as possible. So then you plug that into the computer algorithm and let it do its thing, and it'll basically start making splits in the data. So the tree might find that on average, if we get greater than 25 millimeters, so here, of rain, and greater than 5 millimeters of snowmelt, on average, in that big data set that you fed into it, that would lead to like 1,300 cubic feet per second, CFS, of stream flow. So this final prediction is just going to be how much stream flow can we expect when, on average, we get like greater than 25 millimeters of stream flow and greater than 5 millimeters of snowmelt. Versus maybe the model finds that when we get greater than 25 millimeters of rain and less than 5 millimeters of snowmelt, on average, based on that training data set that we fed in, that will lead to 1,100 cubic feet per second of stream flow. And then the model will kind of fill out the rest of the tree from there. This is quite a simplification of the actual tree that would be built, but this is like the basic gist of it. So then on days when you know what rainfall is, you know what snowmelt is, but you couldn't get out to the stream to measure stream flow, you can, oh, sorry, I lost my chat for a second. Okay, you can plug it into this tree that has already been built and say, in this case, we got less than 25 millimeters of rain, greater than 10 millimeters of snowmelt. So the model is going to predict 1,000 cubic feet per second of stream flow. And on average, based on all of this historical observations, that's our best guess of what stream flow will be on this day when we couldn't go and measure it. So I want to just do like a quick exercise just to check kind of understanding here. And if you don't know the answer, that's totally fine. But I want to ask, so if we got 27 millimeters of rain and 2 millimeters of snow, can you guys guess what the model will predict stream flow will be? It'll be one of these 4 values. I'll give you guys a second to think about it. And then if not, I will just tell you the answer. Someone said 1,300. Someone said 1,100. Someone said 1,100. Yeah, so 1,100 is correct. So in this case, we got greater than 25 millimeters of rain, but less than 5 millimeters of snow. So the model would predict 1,100 cubic feet per second of stream flow. So the difference, why it's not 1,300 is because when you look at snow, hold on, I got a question. Oh, okay, I'll answer that in 1 second. We got, so if we had gotten greater than 5 millimeters, so if this was like 7 millimeters of snow, it would have been 1,300. So Gabby asks, is 1,000 cubic feet per second a lot or a little? And that's a great question. And the answer is that it really depends on what river you're looking at. So if you're looking at like a really tiny like stream, 1,000 cubic feet per second is like a ton of flow. But if you're looking at like a super wide river, 1,000 cubic feet per second is going to be like look quite low when you're looking at that river. So for context, I think that the White River average flow, I want to say, is 1,300 CFS, but I don't want to lead you astray. So I will check that after I finish talking and see if that's accurate or not. That's my best guess. So this is a decision tree. And then a random forest is just a forest of a bunch of those decision trees. So you would just build, like in our case, we built like 150 different trees, and each tree is trained on a slightly different subset of the training data. So that's because if you take just one tree, it has a tendency to be really good at predicting the data that was used to build it. But then when you throw something kind of new at it, it doesn't really know what to do with it. So by building a bunch of different trees, which are all trained slightly differently, you can kind of avoid that problem. So we're going to first use the random forest model to answer the first question, which is what drives stream flow and flooding in the Northeast. So we can use the random forest. We already know that we can use it to predict stream flow, but we can also use it to answer this first question. To measure the importance of different drivers of stream flow, we can get like an importance estimate from the model. And we get this by running the model like normal, and then we would remove the variable of interest. So we would like say like, okay, I'm going to take rainfall out, and then I'm going to measure how much worse the model does at predicting stream flow than if I had included rainfall. And you would do this for each variable one by one. So you're like, okay, I'm going to run the model just totally normal. I'll test it to see how well it does on like a different little data set. And then I'm going to remove snowmelt and run it again and test it again. And if the model does significantly worse, then we know that snowmelt is really, really important to predict stream flow, and therefore is a really important driver just in the overall system. And then we also, important to note that we divided our model into a cold season and a warm season. The cold season is November through May. This is a time period when we think that snow might be important to stream flow. And then the warm season is June through October. And this is a time when there's like no snow on the ground. Snow is not really going to play a role, so we have to look at other variables instead. So for the White River, we find that in the cold season, the two most important drivers of stream flow are rainfall and snowmelt. And in the warm season, the two most important drivers are rainfall and soil moisture. So these are the things that we need to look at into the future if we're going to estimate how stream flow is going to change in the future. In the Shenandoah River, so that's the one that's like way down south, it's in Western Virginia. In the cold season, only rain is important because it's so far south that snow just doesn't really play a huge role. And then in the warm season, rain and soil moisture are still quite important, both of them. So we answered my first question of my thesis, which is what drives stream flow and flooding in the Northeast. Here we're focused on just two rivers. In reality, I did, 4 rivers at a bunch of different locations. But for these 2 rivers, we've identified what is going to cause high stream flow or flooding. And it's going to be when rain and snowmelt are high in the cold season for the White River, or when rain and soil moisture are high in the warm season for the White River. And for the Shenandoah River, it's going to flood when we have just really high rain in the cold season, or we have high rain and high soil moisture in the warm season. So now let's get into the second question, which is how will these drivers and therefore stream flow change in the future under climate change? So we don't have to do a poll here. We can just put it in the chat. Do you guys think that in the Northeast, in the cold seasons, November through May, do you think it's going to be drier or wetter? Do you think we're going to get more rain or less rain in the cold season? Alice says wetter. Anyone else have any ideas? Oh, Ezra says drier. No, one more person to round out. Oh, Gabby says wetter. Okay, I'm not going to tell you yet. Oh, Amelia says drier. Oh, okay, we have controversy. But okay, I'm not going to tell you. Oh, Alyssa says both droughts and floods will be more extreme. Interesting. So this is for the cold season. Same question for the warm season. So this is the summertime. Do you guys think it'll be wetter or drier in the summertime? I'm curious to see. Okay, Gabby says drier. Alyssa says drier. Ooh, Ezra says wetter. Okay, still some controversy. Okay, so I'm not going to tell you the answer right away. You'll have to wait and be in suspense for a minute or two. First, I want to talk about how we can even find this out. And the answer is through the usage of global climate models. So a global climate model is just going to solve a bunch of sets of equations and like physics equations and stuff like that in order to predict climate way into the future over the whole world. And the only thing that changes in the model is what we call a forcing. So in our case, that would be greenhouse gases. So we would say, okay, given current greenhouse gases, let's just solve for like today's weather. And the global climate model can do that with relative accuracy. And then maybe 50 years in the future, we say, okay, we expect greenhouse gases to be this high. Let's solve it again and see what global weather and climate looks like. So you get like a grid over the whole world, like you see in this figure. And each box kind of solving its own sets of equations. This plot to the left here is just showing different scenarios for future greenhouse gases. They're called the representative concentration pathways. They're from the Intergovernmental Panel on Climate Change. And what we're seeing here is like, if we look at the green line, that's RCP 2.5. This would be like best case scenario. Everyone becomes super sustainable. These huge corporations kind of smarten up a bit. And greenhouse gas emissions really plateau versus RCP 8.5. This is like the business as usual. No one changes anything. No one cares. This is like the worst case scenario. We get tons of CO2 into the atmosphere by the end of the 21st century. So we can pick one of these scenarios and run a global climate model and say, okay, what is going to happen in the future? So these are two maps showing what the global climate models project will happen to rain over the United States. And I put a box around the Northeast region specifically. So this is an ensemble of global climate models. That means that you just take the average of like a bunch of different models because every model is going to have its own bias. And in general, the global climate models project a much wetter future in the winter and slightly wetter, but much disagreement in the summer in the future. So this is what the global climate models project. But global climate models do have some drawbacks, mainly just the fact that because they are global, so they are making projections for all over the world, they have to do it at quite a low resolution. So if you look at, back aside here, if you look at like one of these boxes, you're going to get like one prediction for like the whole state of Vermont because they just can't, they can't like resolve these smaller scale processes because it would just take way too much computer power. So for this project, I ran a regional climate model called the Weather Research and Forecasting Model, or WRF. So a regional climate model will take as input that global climate model. So it'll say, okay, over Vermont, the global climate model says, average temperature will be 20 degrees Celsius. But as anyone who has lived in Vermont knows, temperature can vary quite drastically between like White River Junction and like Burlington even. never mind areas that are even further apart. So the regional climate model will say, okay, I'm going to create much higher resolution projections. So I'm going to get like a projection for Hartford, a projection for White River, a projection for Burlington. But I'm going to do it over a much smaller area, so we don't have to worry too much about the computing power. So this is how a regional climate model works. And we've outlined here our domain, which was the kind of eastern parts of the US and Canada. We ran the regional climate model in the historical period, so that's 1976 through 2005. We run the model in the past because we want to see just how well it does compared to observations. And then we also ran it in the future period, 2070 through 2099, and we ran it following RCP 8.5. So that is like the worst case scenario, no one changes anything situation. So really, really high greenhouse gases in the future. And it's important to note that when I'm comparing historical to future, we always want to compare historical simulations to future simulations. Every model is going to have its biases. So if we were to compare historical observations to future simulations, those biases would kind of get swept up into the changes that you see. So by comparing historical simulations to future simulations, you're kind of like accounting for that bias. And then also important to note, this is just one realization of climate. As I just said, every model has its biases and it's going to solve things slightly differently. So I'm not saying 100% this is like exactly what's going to happen, but rather this is our best guess based on the model that we ran. So let's get into some of the flow changes in the future for the White River. So first I want to show the changes in extreme rainfall that our regional climate model projected across the Northeast. So this is just a plot showing the change in the number of days with greater than 30 millimeters of rain. And this would be between the future and historical periods. So in the cold season, which is the winter, our regional model generally agrees with the global climate models. Oh, Gabby says, I hope the worst case scenario does not happen. I hope so too, Gabby. So this generally agrees with the global climate models and says that the Northeast is going to get much, much wetter in the future. And I just put a box here around the White River, kind of interested in. And then in the warm season, it's much more of a mixed bag. If you'll recall, the global model said it's probably going to get wetter, but it's not really clear. And when we see here, we get some areas of decreasing extreme rainfall and some areas of increasing extreme rainfall. So it's definitely more of a mixed bag in the warm season. We're not just getting these like large scale increases like we see in the cold season. So the summer is a bit more variable. We get more extreme kind of at either end of the spectrum. And again, here's just a box around the White River. So again, you guys can just put this in the chat, but I'm curious, like this is for the cold season and this is increase in rainfall. So based on this, do you think that stream flow in the cold season for the White River will be higher or lower? Jack says A, Alyssa says higher. Yes, exactly. Yeah, Gabby says higher, yeah. So based on this, it's pretty clear that stream flow is going to increase. What about for the warm season? So this is where there's like a bit more disagreement. And if you look over the White River, it's kind of hard to tell. Is it increasing? Is it decreasing? Gabby says lower, Alyssa says lower. Nice, we got some smarty pants in the seminar today. So what we found is that in the cold season, we got our future climate simulations and then we plugged them back into that random forest that we made all those slides ago, that beautiful decision tree, plugged it back into that model. And we found that for the White River in the cold season, we get a 32% increase in just all stream flow and a 93% increase in the occurrence of flooding. And this is driven by increases to rainfall and also increases to like extreme snowmelt events. So this is for the cold season, we get large increases. This is quite concerning. And then in the warm season, like you guys guessed, we actually see decreases in stream flow in the White River. This is driven by decreases in soil moisture and decreasing rainfall over the White River watershed. And we also get a decrease in floods, so that's good. But in general, like a decrease in flows is not ideal because of like things like water scarcity. And it's also interesting to note that when we look at the seasonal cycle, so this is like the average monthly flow throughout the year on the White River. And here we have historical simulations and observations. So the good thing is that the historical simulations line up quite well with the observations. And then if you'll recall, in the cold season, we got these large increases. Oh, I have a question. Let's see. Gabby, are you talking about future weather? Yes, I am. Sorry, so I should, wait, I'll answer live. Okay. So yes, so when I'm looking at, these increases, I'm saying in the future, so that would be 2070 through 2099, we have a 32% increase in all flows and a 93% increase in floods by the end of this century. Oh, Lauren is stepping away for a second. That's all right. Okay. So we have these large increases in floods in the future, in the cold season. And if we look at it, so here I'm just putting boxes around my cold season. So that's November and December here, and then January, February, March, and April and May in this red box. So this is really, really concerning because the cold season is already the time of year when we get the highest stream flow. This, I have discharge in cubic feet per second. That's just like a synonym for stream flow. It means the same thing. So it's just another way of saying that we already get our highest stream flow in the cold season. So it's doubly concerning that we have this huge increase in floods in the cold season. Here's a question. Oh, Gabby, can we decrease the number of floods in the future and how? Okay, maybe I will answer that at the end, if that's all right. But so as of right now, based on this simulation, we can expect an increase in flooding events in the time of year that is already seeing the most flood events in the White River. And then in the warm season, so that would be the summertime. Again, this is already the time of year when we get the lowest flows. So it's concerning that we see this reduction in stream flow because it's going to lead to like more, more droughts, more water scarcity. I bet the people who go fishing probably won't like it. So it's not so great. And so lastly, this is just showing the future. I just plopped the future simulations on top here. And we can see basically what we just described. In the cold season, we get large scale increases in stream flow and flooding, which is not good. And in the warm season, it's kind of a mixed bag, but we do see an overall decrease in flooding, implying that there'll be more droughts in the warm season in the future. Okay, so last thing, we'll talk about the exact same thing, but for the Shenandoah River. So again, this is our river, beautiful river here down in Western Virginia. So quick poll, I put a box around the Shenandoah this time. Do you guys think that the Shenandoah in the cold season will have higher flow, lower flow, or you don't know? And this is for the cold season. And again, this will be for the tiny black watershed that I have the red box around. So Alice says higher, Gabby says no idea. So again, this plot here is showing the increase in extreme rainfall. So you can see that across the Northeast, we get large scale increases in rainfall in the cold season. What about in the warm season? So again, looking at this tiny black outline, do you guys think that warm season stream flow will be higher or lower in the Shenandoah River? We have Ezra says A, Leo says A, Amelia says A, so all higher, higher, higher. Gabby says lower. Liz says lower. Jack says higher. Okay, controversy. So let's look into it. So what we find in the Shenandoah River is that we get these huge increases in stream flow and in flooding throughout the whole year. So in the cold season, we get a 55% increase in all stream flow and a 200% increase in flooding. And then in the warm season, we get 185% increase in all flows and 175% increase in floods. And these are driven mainly by increases in rainfall throughout the whole year and increases in soil moisture in the warm season. So this is really, really concerning for flood adaptation. It's interesting to note that in the Shenandoah River, unlike the White River, you don't see that same like sharp peak in streamflow in the springtime. It does still peak then, but you kind of, you know, it's not as like sharply defined. And that's because that springtime peak is usually due to snowmelt, and the Shenandoah River just doesn't really have a ton of snowmelt to begin with, maybe some from like the surrounding mountains. Oh, Ezra says, wow, I know, right? Scary stuff. So these are huge increases in flooding in this river. And then, you know, we can just plop the future simulations on top here. And we find large scale increases in stream flow throughout most of the year. October is like the anomaly here. But in general, we see like much higher summertime stream flow and also higher wintertime stream flow. This is a picture of flooding on the Shenandoah River in 1996. So in the future, we can expect events like these to become way more likely in this area. Okay, so I'll just say some conclusions, some key points, and then I'd be happy to take any questions. So what we found in the White River, we've gotten more floods in the winter and more droughts in the summer. So it's kind of like what we talked about at the beginning. We're just getting more extreme scenarios on either end of the spectrum. In the Shenandoah River, we just get more floods like all year round, and that is quite concerning. And then in general, we've just found that rivers in the Northeast are very sensitive to future rainfall. As I've mentioned, this is just one possible simulation of climate. There are other models that might simulate something slightly different. But in general, we've just found that like even a small change in rainfall can have a really huge impact on our rivers. And then finally, just my concluding point is we do see extreme weather becoming much more likely in the future under climate change. And that would be extreme flooding, extreme droughts, you know, a lot of the stuff that we talked about at the beginning. So Gabby asked a question earlier, which was how can we decrease the number of floods in the future, or can we? And so I guess the answer to that would be maybe these simulations, we took the worst case greenhouse gas scenario. So ideally, if, you know, as a world, we could limit our greenhouse gas emissions, we probably wouldn't get such a severe outcome as what we've simulated here. But, you know, these atmospheric and river processes are really, really complicated. So it's hard to understand exactly what is motivating these changes, but I think it's safe to say that human-induced climate change is definitely a large contributor.
So I'm going to jump. Oh, go ahead.
Oh, sorry. I was going to say I'll be happy to take any questions.
Yeah. So as you guys think of your questions, I'm going to throw up a poll right now that we always do. Just get your feedback. 2 questions, 1 to 5, 5 being the best. Just rate today's cafe and how much you learned, because this is good feedback for us. And when you're done taking the poll, if you have a question for Charlotte, pop it into the Q&A box and we'll get to that before you all leave today. So just give a moment for all of you to take the poll. And I know there already were some good questions, and I see a question comes in. I'm going to wait a few more minutes to let everyone take the poll. If for some reason you don't see the poll, put your answers in the chat. So it's 1 to 5, 5 being the best, what you thought about today's cafe, just rating it. 1 to 5, 5 being the best of how much you learned today. So I'd like to see a few more people answer the poll because we don't have everybody answered yet. And it's helpful to have you all answer. And again, if you don't see the poll, you can just put it in the chat. And try to get a couple more of you, so please go ahead and do this. And while we're waiting, put your questions in the Q&A box.
Yeah.
All right, I'm going to close the poll. Thank you. So we have a question from Leo. Is anything being done to combat the more frequent and more intense flooding, like flood walls or dams?
That is a great question. First of all, the rivers that I chose are all undammed because dams make the prediction of stream flow really complicated, because instead of like rainfall deciding how much flow there'll be, it's like humans who are deciding it. So it makes it a bit more complicated. But in general, like rivers that do have dams on them are typically more prepared when it comes to extreme flooding, because the dam operators can kind of look at weather forecasts and like modulate. So I guess the biggest concern is for these undammed rivers, like the ones that I talked about today. And what was your other? Flood walls. I haven't heard anything about flood walls being constructed. It's important to note that these are like for the future. So we haven't seen any near as extreme of an increase in the historic, like in the observational record yet. I think there has been an increase in the lower magnitude floods in the Northeast in general over the past like 30 or so years, but nothing so extreme that would warrant like a complete like infrastructure overhauling yet. And then the other question, what is your favorite part of your research? That's a good question. I really love like the coding aspect. I guess I'm kind of like a computer dork, but I just love like the problem solving and figuring out how to model these things. I just find really, really interesting. I've gotten to work with so many amazing collaborators at Dartmouth, so I really enjoy that too. Just kind of being with people who are also just really interested in science and understanding our world a bit better. And I just really love being surrounded by that energy. And, if anyone is interested in going into like academic research, definitely feel free to reach out to me. I highly, highly recommend. It's a lot of fun.
That's great. Good questions. I don't see any other questions that have come in. And again, I would, you all should take up Charlotte. If you think of something later on, you can reach out to her. You can do that through me. I think you all get emails from me that you can respond to. So I want to thank you all for joining us today. Let's all thank Charlotte for sharing her research with us and helping us understand a little bit more about how climate change is going to affect our weather as we move forward. So thank you so much.
Yeah, thank you all so much for coming. I hope you liked it.